Welcome to EEMS 240. This video will demonstrate the graphical features available in EFDC Explorer to set up and configure the Wave module. Let's get started. The influence of wind on the flow velocity field is important while studying hydrodynamics and sediment transport in lakes, estuaries, and coastal areas. Wind effects not only induce the flow current, but also generate surface waves with a height of up to several meters. To calculate the total bed shear stress in such areas, the model must take the wave factor into account. The wave direction is the same as the wind direction. This means that the effects of refraction, diffraction, and reflection are not taken into account in the internal wave model. Now that the wave module has been activated, expand the module tree and right-click on the Waves branch. This will open the Wave Module Setup dialog. There are two kinds of major options for waves, internal wind waves and external wind waves. We will first summarize the internal wind wave options. Two different options are available for the internal wave model of EFDC+, internal wind waves for the boundary layer only, or that impact currents and the boundary layer. The latter option is activated when the Include Radiation Stress checkbox is checked. Upon activating this option, additional options will appear in the Wave Parameters and Options frame. The Wave Parameter and Options frame allows the user to specify KS, the Nicorazzi sand roughness value. This can be estimated by increasing the median grain diameter of the substrate by a factor of 2.5. The Nicorazzi roughness is not the same as the hydrodynamic bottom roughness used by EFDC+ to solve the hydrodynamic equations. The time series for wind speed and direction are used to compute the instantaneous values of wave parameters with fetch calculated for each cell in 16 directions. The effect of shoreline and EFDC+ internal masks are included in the fetch calculations. The resulting wave parameters are then used to calculate total bed shear stress, with bed shear stress linked to the current generated shear stress via the Grant-Madsen approach. The internal wave model is capable of internally generating wind-induced waves for bed shears only. This can also include the radiation stress for the whole water column. These options allow the simulation of wave effects and resuspension of sediments inside EFDC+. Simulation of wind waves can be restricted in EFDC+ based on a defined polygon. Check the Use Subset of Computational Grid checkbox, and the subset polygon frame will appear. Any compatible text or shapefile can be used to subset the cells used for the computation of wind waves. The external wave model option allows the user to import wave parameter fields from SWAN and other wave models. The steady and unsteady wave option corresponds to the type of waves being imported into the EFDC+ model. The steady wave option computes the wave field as a steady state phenomenon, whereby the wave field is an instantaneous function of the wind speed, direction, and fetch. The unsteady wave option requires the wavetime.imp input file and will simulate wave propagation in the system even after winds become calm. The Generate Inputs button provides a convenient GUI interface to generate input files for the SWAN model. To generate SWAN input files, EE provides the user with options to include different aspects of the current model in the SWAN model setup. These include the computational grid, wind forcing, bottom topography, open boundaries, and vegetation. The duration of the SWAN simulation can be set in this dialog as well. At a minimum, the wave model should be run for the period of the simulation for the EFDC+ model. Otherwise, if the wind and open boundary options have been selected, the simulation can be as long as those time series. The input parameters of the SWAN model can also be customized by the user with this dialog. This includes the maximum number of iterations and the inclusion of bottom friction. If the Open Boundary Conditions checkbox is checked, then the Boundary Conditions button is enabled. Existing boundary conditions in the model are listed in the frame on the left. Wave boundary conditions can be optionally included for each open boundary group. There are 3 options to set forcing type from existing boundary conditions of the model, as no wave, constant, or time varying. The constant forcing type supports a simple constant wave field to be provided at the selected open boundary. The user must provide the wave height, wave period, wave direction, and direction spreading value to complete the setup of the constant wave field. Time-varying boundary conditions can be provided to the SWAN model by pointing to a valid time series of wave height, period, and direction. In the Export SWAN Input Directory frame, the default SWAN input file will be created and saved in the hash analysis folder of the current model input directory. The user can also specify this path using the Browse button. Now that the input file settings have been configured for SWAN, we can hit the OK button to generate the input files. After the SWAN input files have been created, the user can now run SWAN by clicking on the Run SWAN button. Once clicked, the SWAN Run Options form will appear. In the SWAN model input field, browse to the input file for the SWAN models. By default, these are located in the hash analysis folder of the model. Before attempting to run SWAN, ensure that the SWAN executable path points to the executable file in the SWAN folder of the EMS installation folder. Once the input file and executable path have been provided, click the Run button to launch the SWAN executable. 3 additional options are available for linkage to external wave models. The Use Existing Wave.imp option imports an available wave.imp file from another project into the current project. If selected, the user must ensure that the 2 projects have exactly the same grid. Within the Create Wave.imp option, there are 3 sub-options. Import from existing Wave.imp option will prompt the user to locate an existing Wave.imp file. However, the grid associated with the existing Wave.imp file must be the same as the current model being configured. In the Convert from SWAN Results frame, the user should first decide if they are using steady or unsteady waves with the drop-down box. If steady waves are used, then EE does not require the wavetime.imp file, as the waves are at a regular time interval and the option to load this file is disabled. Alternatively, if unsteady waves are being used, then use the Browse button to set the path to the SWAN model outputs and select the wave time file. Next, there are 2 options for SWAN input in the Using Output Options frame. The For Same Grid option requires the SWAN model to have the same grid as the current EFDC model and uses the group file from SWAN. The For Location option uses the data as XY points. This option should be chosen when SWAN and EE use 2 different grids and the wave data was exported at the locations from the SWAN model. The latter option requires 2 input files, a location file and a table file. Both files should be generated by the SWAN model. For sparse location points, interpolation to the grid is suggested. Options to configure the interpolation can be found in the Interpolation Options frame. If the original grid or points were dense relative to the EFDC grid, then simple averaging with cells can also be used. Pressing OK will complete the conversion and import process. The user can also manually configure the input files for waves. The user must match the input data file to the parameter specified on the drop-down list wave field parameters. The user can either have wave height, estimated as 2 times the wave amplitude, or wave energy. EE will compute one from the other. The user has the option of using a polygon to select which EFDC cells will be used for the assignment. If a polyfile is not selected, then the assignment operation will be for the entire model domain. EE interpolates and converts the wave model results into the format needed for EFDC+. The interpolation process has 2 options, nearest neighbor interpolation or cell averaging. Once the setup of the wave module is complete, you can save the model and run the EFDC+ simulation. Thank you for watching. You can find the link to the next video below.